Okay, and a good morning to everyone as we bring it down. And that was the infamous Bruce. And what was our title cut there?
Brilliant disguise.
Brilliant disguise. That means these skies are brilliant blue?
Yes.
Uh-huh. You rolled your eyes on that. I saw that. Okay, we are working in Chapter 6. We did yesterday the presentation in 6.3. I told you today that I would go ahead and answer questions on 6.2 and 6.3 today before we do anything else. There was some concern expressed about 6.1 and 6.2 being open yesterday afternoon. Is that right, Wilmaro? And I'm trying to check on that now. Unfortunately, there, finally, it comes up 2 minutes later than I'd like, but I'll check that in the computer in a moment. Michael.
Can you go over that process you did with the multiplication?
Go over a process with multiplication with?
It was decimals to the third power.
Decimals, okay, I've got it. I know what you're talking about. Okay, now I can check on something that Bulmara was asking about. Okay, 6.1 I only had until 11 a.m. on yesterday. 6.2 should have been open until today, midnight. Should not have closed down on you. Yeah, 6.1 would have yesterday at 11 a.m. I did not have that open. I asked if people needed 6.1. Well, I had it closed here at 11 a.m. was when I had it set to close yesterday. If it went longer than that, it was still open? It should have closed yesterday morning, and you're saying that you needed it open. Okay, I understand. So if that's the case, if you'd said something to me yesterday, I would have tried to make sure it was open. I'm doing that now, and so you need it open, and this is what, Thursday? So what I will do, is today enough to open it up that far? Or do you need it more than that? You want everything until Saturday? Well, I don't know about everything, but at least I can make this do. I'll open this up until Saturday. I just did that Saturday midnight. And as that's on 6.1. And 6.2, as it stands right now, just to give you the date and time that's open, on 6.2, we have that open today. I assume that would be comfortable if you had that likewise a little bit later. So I'll do the same thing there. It'll just take me a moment to do that. We'll get that out of the way because right after this class I have yet another lecture to do. So let me finish this up, and I'm doing this also to Saturday. Okay, so that's done. That's Saturday at midnight. So that should give you time to get 6.1 and 6.2 done. The way it stands right now on 6.3 that we talked about yesterday, you have on 6.3, that is until tomorrow, Friday at midnight, I guess. And if it's going to be necessary beyond that, you can tell me at the tutorial tomorrow. Okay? So with all that done, I have a request for a problem where I had a decimal value to an exponent, I'm assuming.
Yeah.
Okay, so let me just mess something up here on the board just as a typical. We'll see if it answers what you want to talk about. So let's say I have something like maybe a negative just to make things interesting, and a 0.03, and I'm going to take that to the 5th power. That's what we talked about yesterday. Now I could make this more interesting, I guess, by going to the 15th power or the 30th power to try to get to the, well, to get the idea that you probably don't want to do what I'm doing now, although this is your alternative. But if I had more than 5 factors, I think you would agree that this is going to get a bit tedious. Now, this is what you have to do with one approach. Now, my argument is that we have 5 factors, so our value is going to be negative. And what I wanted you to consider is that this is 3 times 10 to the minus 2. And we're doing that to the 5th power. Now, using the rule we talked about yesterday, a, b to the nth, a to the nth, b to the nth, then this becomes a minus 3 to the 5th times 10 to the minus 2 to the 5th power. And then you multiply these exponents and you get minus 10. So this is 3 to the 5th times 10 to the minus 10. Now the only thing I would go at this point, I'm not sure I want to move the decimal point 10 places to the left, but I first need to do what? Get 3 to the 5th. 3 squared is 9. 3 to the 4th is 81. Multiply by 3 again, 243. So I have negative 243 times 10 to the minus 10th power, and I would be very happy with that answer. Now, it's not in scientific notation, but it's a very adequate answer. I would just move the decimal point that right now is after this 3 back 10 places. Now, if you want it in scientific notation, this is going to become a negative 2.43 times 10 to the minus 8. Because 10 to the minus 2 would move it back to here, and 10 to the minus 2 times 10 to the minus 8 is 10 to the minus 10. Now, if you sit there and do this, it's going to get pretty tedious because you're going to have then you're going to have a total of 7 zeros before you get to your 243. Now, I can do it, your choice, but this is where I believe the algebra is as opposed to the arithmetic you're doing up here. Does that answer it for you, Michael?
Yeah, I like that way.
This way? That was my hope, that would, as I say, if I didn't hit it hard enough, I could go to the 8th power or the 9th power, and that would have been even worse. You're sufficiently impressed. Okay, Jessica.
Okay, I'm trying to understand something, but when you get, you know how,
Okay, I'm talking about moving the decimal over.
so every time you do that, you know how it's to the 5th exponent, you're putting 3 to the 5th, right? And then after that, then you're doing 10 to the negative,
Get the negative 10.
so that's what you're going to do every,
Well, I'm using again what we said yesterday, and I'm going to do it this way this time. Let's say I have, first I'm going to write the one I did yesterday, then I'll write it. I'm going to get too many letters if I'm not careful. A to the n, b to the n. Now the problem was I had a b which was already to an exponent.
okay, that's what
So this was in the form of like saying a to the r, b to the s, all to the n. So that's a to the rn, b to the sn. That's essentially what it became. Okay? Okay. Okay with you, Michael? Anybody else with the problem from 6.2 and 6.3? No? 6.2 and 6.3. I thought there would be more questions. I'm surprised. I'm pleased. But I really anticipated more questions than that. I'm happy. Okay, I'm going to come back center and very pleased. My goodness. We talk about trying to anticipate difficulties. And what I'm going to do now is go to 6.4. Now, this is where life gets a little less fun, maybe. Okay, dividing decimals with numbers and, well, decimal numbers. That's not bad, but here's the one that's interesting. Square roots. Let's talk about them. First, problem with square roots. First problem with square roots. Is the square root always smaller? My question, is the square root always a smaller number? Will you write down an argument for that on paper? Give me an example for your argument. Is the square root always a smaller number? Write down something on paper for me. Ephraim, on paper, answer my question. Is the square root always a smaller number? And I want you to give me an example, and I won't discuss until you write down something. Is the square root of a number always smaller? That's my question. Smaller, meaning a magnitude, not necessarily less digits. But is it a smaller number? Always. That's my question. Is the square root, for example, take a whole number. Start with 25. Square root of 25 is 5. Give me a counterexample why the square root's not always smaller, if you're going to argue that. Sandra.
3.
Square root of 3? What's 2 times 2? 4, so it's going to have to be smaller than 2. So the square root looks like it's smaller.
2. It could be 2.
No, square root of 3 can't be 2 because 2 times 2 is 4.
No, I'm saying the square root of 2 then.
Okay, the square root of 2 is 1.4.
Oh, then no.
No what?
No.
Is the square root of a number always smaller?
Yes.
Hold on. Hold on. Stay with the square roots. I've got a lot of discussion going on. Give me a case where a square root's the same number. 1. Square root of 1 is 1. Therefore, the square root's not always smaller. Okay? Let's go to the board on this. Is the square root always smaller is my question. And I had the square root of 1 equaled 1. So clearly the square root's not always smaller. It is often. The square root of 64. 8. Hold on. Just stay with me. Emily, hold on. Just stay with me for a minute. I've got the square root of 64 is 8. Smaller number. Square root of 25. 5. Smaller number. These are nice because they are perfect squares inside. Now, if I go to the square root of 2, that turns out to be 1.41 with a whole lot of garbage after it. It never ends. But it's a smaller number. Square root of 0. Oh, there's a square root of 0. 0. Because 0 times 0 is 0. Square root of 1 is 1 because 1 times 1 is 1. Square root of 1/4? No, it's not 1/8, and I won't say who said that. 1/2. Square root, not square of. What number can you square and get 1/4? 1/2 times 1/2 is 1/4. Therefore, the square root of 1/4, bless you, is 1/2.
I don't understand that. Because wouldn't 1/2, oh, no, that'd be 1/2 plus 1/2 would be 1.
I'm not adding, I'm multiplying. We in agreement now? It's straight. No, that's why I asked the question. And that's what makes this section most interesting, because this fraction changes our whole idea of what a square root is. We think it's smaller, but here it is suddenly bigger. A little bit non-intuitive. Okay? What is the square root of 1.44? You again are taking numbers incorrectly. Nope. 1.2. Because if you multiply 12 times 12, you get 144. and you'd have 2 digits after the decimal point. 1.2 is smaller than 1.44. That works. But what about this one? Same question I just asked before, right? I had 1/4, and that was 1/4. So if the square root was 1/2, indeed this is 0.5. Shamra? You grumbled there. This is 50, if you like, and 0.50 is larger than 0.25. So square roots of numbers between 0 and 1 exclusive are going to be larger than the number themselves.
Why is that though?
Has to do with fractions. When you take a part of a part, you get something smaller. So when you square something, you're multiplying a fraction of a fraction, you get something smaller in pieces, right? I take a half of a candy bar and take a half of a half, and you get a quarter. Okay? And the reverse process is the square root. Otherwise, when I get the square root of 1/4 and I say it's 1/2, my argument is that 1/2 times 1/2 should give me that answer. So a 1/2 times a 1/2 will give you a smaller number, even though 2 times 2 is a larger number. Oh, but this isn't the square root of 0.50. It's the square root of 0.25. This is the square root of 0.25 because 0.5 times 0.5 is 0.25, Natalie.
How would you do the square root of
4/16. I wouldn't necessarily reduce it. I could. But I can argue that that's the square root of 4 over the square root of 16, which is 2 over 8, which is 1/4. Down a little bit more. Okay, thank you, Jennifer. There's the 1/4. Okay, because if I had, now did I get that right? 2 over, no, Curl, you did a very bad DAE. How about 2 over 4? I was listening to Sandra's doubling when she said 8 on some of the problems. So that should be 1/2, correct? Because that is 1/4. Okay, so reduce and then take the square root. Now, I'm using this statement. The square root of a over b is the square root of a over the square root of b. Now, caution. When you say, thinking in terms of problems that students have, when you see the word square, you think of multiplying something times itself. So when you see the word square root, in your head, the first word you hear is squaring something, and so you tend to multiply it by itself. So if I ask you for the square root of 9, the error that I often hear is 81, because you're hearing the phrase square something. Now when you see it written, it's not as often confused. But if I ask you to take the square root of 9, which should be a 3, you just hear the word square. Now, the other thing you have to be careful of is don't use the phrase root 9, because there are cube roots and fourth roots and fifth roots. So, example. The 3 is called an index. That is saying take the third root of 27. So name me a number that you can write as a product 3 times. Factor is written 3 times so that you'll get 27. The answer is 3. 3 times 3 times 3 is 27. So the third root of 27 is 3. When you say square root, you're really understanding that there's a second root. The index is a 2. And it tells you how many times you have the factor in the resulting product to check your work. So the square root of 9 is 3 because 3 squared is 9. The cube root of 27 is 3 because 3 to the third is 27. Okay, with that preamble, let's see what kinds of problems are in this section. Because square roots of decimals can get us into some trouble. Evaluating square roots. This is on page 444. And here are just some illustrations of why the square root of what's given is the number. It's sort of working backwards. The square root of 64 is 8 because 8 squared is 64. Now, something's missing here. Simply a square root symbol, correct?
Yeah.
Okay, the square root symbol's missing. I didn't note that until just looking at it in the screen. That's supposed to, finish. Will you write that in correctly? Not incorrectly meaning wrong, but write the number correctly. You need a square root symbol. So what you need to do to this is bring this down and do that in your book. Otherwise, it makes absolutely no sense. Okay, so that's the square root of 100 over 121. That's 10 elevenths because 10 elevenths times 10 elevenths is 100 over 121. We okay there? The square root of 2 we just talked about. And I've shared with you that that is what we call an irrational number. We proved that last Monday. We took time to do that, and that's where those of you who went to Sacramento, I have encouraged you to watch that tape because we proved the square root of 2 was irrational. Now, the proof wasn't very rigorous. There are a few parts in the proof that I would like to tighten up. That is, if you square something and you get an even number, then what you squared has to be even. Now, we argued that. So we said if you square something and it comes out as 2 times something else, that means what you have squared is even. And I argued, therefore, the number I squared had to be even itself to get an even. That was not very rigorous. That was arguing on what I hope is your intuition. But we said that the square root of 2 was an example of what I have here on the screen in bold print. Irrational numbers. Numbers that cannot be written as a common fraction. And so you have a definition as I slide this down. Irrational number. A number that cannot be written as a over b, where a and b are integers and b is not equal to 0. Irrational numbers. Then, something I've said to you before, all the way back in 10, and this is at the heart of algebra, the real numbers. The set of rationals and irrationals put together. So that includes anything I can write as a decimal, whether the digits repeat, terminate, or do neither of the above. Okay? Real numbers. Now, with the exception of the one property, which I called Emily's property, where we said for every number, there is a number called 1 over that number. We call the inverse of multiplication, so that the number times 1 over the number gives you 1. It's Ritchie's reciprocal. You have 11 properties when you kick that one in of the real number system. So the properties we went through: closure, commutativity, associativity, identity, inverse, distributive. There are 11 of them. We call those the 11 properties of the real number system, and we argue every number in the real number system satisfies those properties. That's the assumption in algebra, that you have a real number system. Before I leave it, you need to understand there's more to numbers than that. I'm going to write a problem on the board. A squared minus 1 equals 0. What values of a make that true? Look at the board and think about it. What else? 1 and minus 1? Will you agree? Listen to what's being said. You have whatever's here is squared. You got caught in this in your last test. Whatever is going to be replaced with a is squared. So if I have minus 1 and I square it, minus 1 squared is 1. Subtract 1, and do I get 0? No, what about 1? Regular 1. 1 times 1 minus 1, that's also equal to 0. Okay? So 1 and negative 1 both work. Two solutions. What is the degree of the expression on the left? Second degree, correct? The exponent is 2. So again, the degree of this expression on the left is 2. It is called a second degree equation in one variable. Okay, now I'm going to take you one step further. That's basically one of the most important concepts in algebra. It was done by Carl Friedrich Gauss, who did just about everything in mathematics. You heard of degaussing the TV tube? Well, that's the same Gauss we're referring to. But Carl Friedrich Gauss said that if this is second degree, there are going to be two solutions.
So any second degree?
Any second degree equation, when one variable, has to have two solutions. And he did that essentially as a doctoral dissertation at 18. He was bright. Yeah, he was bright. Disgustingly bright. Okay. Now, I need to go to the other side. So, Jennifer, if you'll give me camera 1 here. Let's come back to the document cam in between. We're talking about irrational numbers, and my point is we morphed that into real numbers. We said we have rationals, we have irrationals, and we call those the reals. And my question, is there more to life than the real numbers? And the answer is yes. And it has to do with this statement, that if I had a squared minus 1 equals 0, the argument was there's two solutions. Okay? I'm going to change the problem. And Gauss said this still had to have two solutions. Now, if you take something that's positive and add a positive, can you get 0? No makes sense. If you have a positive, I add a positive, a squared is going to be positive. Add 1, so Gauss must have been wrong. No. We create a new number system just for Gauss. Well, that's not bad, but that's not what they're called. I want a squared to equal minus 1. So a is the square root of minus 1. And we have a name for that. Now we have iPhoto, iPods, right? iMacs. Here's an I number. I. I is the square root of minus 1. And when you square I, you get minus 1. So I squared is equal to negative 1. Yes. We call this, yes, a would have to be I in order for a squared plus 1 to equal 0. And there are two solutions, because minus I squared would have to be minus 1 times minus 1, which is 1, times I squared, which is minus 1. They're called the complex numbers. And just for your information, I is called imaginary. Hence the word I, or letter I, for imaginary, an imaginary number. And that's what you do in algebra. So we carry this a little bit further. So the real numbers are a subset of the complex numbers. Okay? Yes?
Where does this imaginary number come into play?
In the theory, because Gauss wanted to say that for every second degree equation, one variable, there had to be two solutions. The only way that could be true is if we created a new number system. Okay, so that's the first obvious need for it. Then we go to three-dimensional systems, which involve I, J, and K. And they get used in physics. There's a lot of things in trigonometry, in physics, that involve the complex numbers. And I don't want to go beyond that at the moment. But we could spend several weeks having fun. James, you had a question? You didn't. It was Marisol. I just saw a hand up somewhere.
It was like 8 to the third instead of 8 to the second.
If I had a to the third minus 1 equals 0, there would be three solutions. Now, it looks like one's the only solution that will work. However, there are two complex solutions. And they aren't as simple as just little I. Okay? There's a neat problem I used to do called the 5 roots of 1. This equation. And it was a very interesting number, and spent an hour just doing that alone, but it was a trig problem in trigonometry, which is sort of past geometry with right triangles. But what Gauss was saying is that this has to have 3 solutions, this has to have 5 solutions, and in this case, one of them is your usual number 1. Then there are 2 complex solutions. Here you have 1 real number solution and 4 complex solutions. So I want to leave it at that, or I'm going to get myself deeper than I want to be. Let's go back to the document camp. I just want you to realize that we go beyond real numbers. We go to complex numbers, and at the end of a math 70, you'll be into the complex numbers because they're so much fun. Here is what we just did. Let's look at this now. I'm on page 445. Will you turn to 445? 445. Those are 3 problems, just like the ones I did in the board. They're a little bit harder. Now, the second one, I did 1.44. Here's 1.21. That one's not bad. But notice how difficult they're getting when you get down to 0.0064. Not so easy, correct? So the question, is there an easy way of doing that? So leave that on the screen, and this goes just a bit beyond, but I don't mind taking you beyond. Beyond's nice. Yes, beyond and into infinity. The square root of 0.0064, my argument is that's 0.08. Now, that's not going to be an easy thing to see necessarily. So what I'm going to do is a little different idea. Skip that for a moment. Watch this. Square root of 10,000. I hope you realize that is 100. Okay? We have another way of writing square roots with exponents. You've seen exponents that have been negative, correct? We've been doing that. We know what that gives you, a reciprocal. Okay, now they can become fractions. So if I tell you that I have the second root of a It is a to the 1/2. Now that's going to be our agreement. It's not why, it's just that's our agreement. Now does it work? 10 to the 4th to the 1/2. What am I supposed to do with exponents when they're like this? Multiply them. I thought that's what you meant. And what's 1/2 times 4? It's not 8. It's not 16. 1/2 of 4 is 2. 10 squared. And indeed, the square root of 10,000 is 100 because 10 squared is 100. That's nice stuff. It was just some number. I'm just using a letter to represent a number. Just like I said, a to the m to the n, I'm saying that that is understood to be a to the m times n. So I'm saying if you have the square root of a, I can write it as a to the 1/2. I can put b there, and b, c and c. It's just like it's a letter that I use to represent some number I don't know. Sometimes we use x. Okay, back to here. What are you going to do? 0.0064. Can you rewrite that so that I could use this idea? Here's the number I have. Now I'm going to argue that this is the same as 64 times 10 to the minus 4. Do you agree? See that? Because this says move the decimal 4 places to the left, the decimal's here after the 4. Okay? But that means I have 64 times 10 to the minus 4 to the 1/2. But that's 64 to the 1/2 times 10 to the minus 4 to the 1/2. This says take the square root of 64, which is 8. 10 to the minus 4 to the 1/2, multiply, and you get negative 2. Answer 0.08. Make the exponents work for you. Now, this sign has nothing to do with whether the answer will be positive or negative. It just tells you how far to move the decimal point. Minus 1, I have a minus 4. So what is 1/2 times minus 4 over 1? Down to chalk that is not at all. Agreed? Just an arithmetic problem. Now, to think your way through, as we look at this backing up, if you look at this 0.0064, and you have to just realize that I have to get a 0.08 so I can eventually get that number, I don't think that's very easy to see. But if you understand what a square root means with an exponent, life gets easier. Now, again, I'm rattling that same debate. I'm going to leave that here, and then take camera 1, if you would, please, Jennifer, and come back to here. This is the same argument we're battling. You take this problem and you do this, or you can do this. Do you want to make the exponents and the algebra work for you, or do you want to pay your dues the hard way? And I'm giving you a choice. If this is the only way you like this problem, you'll get through this course okay. But when you go into 70, you're going to be expected to go the next step. Okay, back to the sideboard. If you can see that 0.08 is the answer to this, that's good. Now, is there an in-between those two extremes of seeing it or using the exponents? And the answer is yes, if you'll let me use fractions. But fractions are good. They're friendly fractions. Okay, I'm going to slide over here now. How would you read 0.0064? as verbal notation. 64 what? 64 tenths, hundredths, thousandths, 10,000ths. Like this better? Because this is the square root of 64. This is the square root of 100, or 10,000, I should say. And the square root of 64 is 8. The square root of 10,000, 100. What is 8 hundredths? Huh? 8% too, thinking of it that way, 0.08. Somewhere in there, I hope you find comfort. This one is selling better. No, I know. I got to find something that you're comfortable with to go back to until you get comfortable with something new. Okay, eventually this will get comfortable, but in doubt, go back to your friendly fractions, and they will save you. Yeah, see, it's all a matter of perspective, right? Pain is a matter of how much fun you're having. Okay, let's leave that there. So we can do these in a variety of ways. On page 445, where those problems were, these were the problems we just talked about, trying to defend each of those answers, I think you might look at it now and say the first one. You could have written it as 9 over 100. The square root of 9 is 3. The square root of 100 is 10, hence 3/10. Okay? Same idea again. Let's go back one more time, Jennifer, because that didn't sell. Here's my number. Stay with me. This is 9 over 100. The square root of 9 is 3. The square root of 100 is 10. 3 over 10 is 3/10. Got it? So, give me the answer for this one, how you would argue it, because this is a technique that's being used in your book. This is 0.0081, so what would you argue? That's 81 what? It's the 10,000ths. 80. It's still 0.0081. That's tenths, hundred thousandths, 10,000ths. Now, what your author is arguing, you have 4 digits after the decimal here, so you're only going to have 2 after the decimal here. That's the rule. 4 digits after the decimal point goes to 2 digits after the decimal point. Why? Okay. If I have 0.0081 square root of that, I'm arguing that that is the square root of 81 times 10 to the minus 4. There's your 4 digits after the decimal point, correct? But if I'm saying that this is the same as 81 to the 1/2 times 10 to the minus 4, that's to the 1/2. That's where you, in essence, are multiplying 4 times 1/2. You're dividing 4 by 2. Back to the document, Cam. That's why, if you have 4 places, just divide by 2, and it tells you how many places you want after the decimal. Because the square root is a half power as an exponent. Robert first. If there weren't an even, very good question. Okay, let's come back to the sideboard. We can tweak that a little bit. Let's say I had the square root of 0.00081. Okay? That's 81 what? 100 thousandths. Okay? So that's 81 times 10 to the minus 5. Okay? Now, the answer I'm going to give here has some real power to it from this extent. When you go from a math 70 to a math 90, you hit a thing called logarithms. They're just exponents. Okay? And what I'm going to do here, I would come back and reference as an example of what I would do 2 semesters later. Okay, so I just want you to understand the question you've asked is going to matter a little cleverness here. What I do is say, I don't like that minus 5. It's odd. I'd like it to be even. So why don't I rewrite this as 8.1 times 10 to the minus 4? I make the place value, well, first I make this an even exponent, so I know now it's going to be 10 to the minus 2. My problem is I've got to get the square root of 8.1. And that is not something that's a whole number. I have to find a way at some point of getting square roots of things that themselves are not perfect squares. Now, I showed you how to take the square root before. Remember, I did that problem where we took the square root of a number and we doubled the number of places, and that's a long time ago, where I took a square root of any number you want. There's an algorithm. There's a process we can follow. Or algorithm. Okay, A-L-G-O, rhythm. Algorithm. The argument is we would put this in a calculator at this point. But we would have used a set of tables in another lifetime, where you would have had a table giving you a number for here. So, for the moment, we are going to restrict, obviously, our problems to where things can be done nicely. So we make life pleasant for you, so you don't have to deal with this. And again, I am not wanting to use the calculator right now. I'm wanting you to do things without a calculator. And of course, this opens up the door. Well, if you look at this problem here, you get a pretty good idea of it. Because if I look at the bottom of 445, that 2846, the square root of 8.1 is 2.846. Otherwise, he used a calculator to get that. Okay, back to the problem just a moment, Jennifer. Because this is 81 times 10 to the minus 3, correct? So I can write it as 8.1 times 10 to the minus 2, and then it's the square root of 8.1, decimal move one place to the left, and so that tells you the square root of 8.1 is that 2.846. You get it in a calculator. Yes?
That equal sign to the non-repeater.
Okay, let's look at the sign. Michael picked up on a symbol here. Double tilde. That means approximately equal. There is no exact answer for that. That's a decimal that goes on, does not repeat, does not terminate. It goes forever and ever and ever. I hope this, okay, just a minute, I need to, there. There is your number. 2.846049894151542, more garbage to come. That's your square root of 8.1. You just put in 8.1, and with the calculators that are just what we call the basic 4-function calculator, here's one that you used before, there's your square root key. So you just put in 8.1 and press that key and get the answer. Now, our effort here is not to, again, understand how to do things in the calculator, but there are points at which you would resort to a calculator to get an answer. So if I look at something like this, Let me get this down a little bit flatter. Here's my number. What is your cleverness going to be? Try to write, well, first, do you recognize 196 as a perfect square? You may not. What's 15 squared, coming off there for a moment? That one you should know with the shortcuts I've given you. 15 squared. Square any number ending in 5. What do you do? 35 squared. How do you get the answer? Add 1 to the 3. That gives you a 4. 3 times 4 is 12. And then put a 2-5 at the end. So 35 squared is 1225. Okay. Now, what's 15 squared? 225, correct? 196 is smaller than 225, so the square root has to be smaller than 15. You think it might be a 14 because 4 times 4 is 6. It is. Come back and look at the number again. Multiply 14 times 14, and I believe you get 196. So the only question is, can I write this? I know Jennifer's going back and forth here, but if you write this, 196 times 10 to what power? Nope. Nope. 10 to the minus 6. 196 times 10 to the minus 6. Because you go back 6 places. So if I write it as 196 times 10 to the minus 6 and take the square root, I'm going to have 14 times 10 to the minus 3, which would be 0.014. There's your answer. Now the question. Is that just going to pop in your head? Probably not, because you don't know your perfect squares well enough. But I would review for this set 12 squared, 13 squared, 14 squared, 15 squared, 16 squared, and so on. Okay, division. Now, there's some things I haven't said, and I'm running out of time here, and I'll talk about some of them tomorrow. Here's a division with polynomials. Okay, now, if you're going to do this, okay, in terms of a division, how would you write it? How could you write it? I have 8.2 into the 6th divided by 2.5 into the 2nd. What would you do as I come up to this space here momentarily with camera 2? Just a fraction. Let me write 8.2. And I'm going to have what? A to the 6th over 2.5 and a to the what? Is that an n? Oh, those are n's, not a's. I was looking at the monitor and seeing a's. N to the second. So what could you do here? Subtract the exponents. So it's going to be n to the 4th. And then I'd have to do what? Divide 2.5 into 8.2, and that's not going to be very pleasant. Well, yeah, you'd write it as 8 and 2/10 and 2 and 5/10 and deal with fractions, and that would work nicely. Or you can just divide 2.2 into 8.2, move your decimals around. So we need to talk about that. Okay? And just a reminder, I have not taken time to talk about how you divide one decimal into the other. I'm assuming that that is something that we remember from last semester. So if not, that's something you'll want to review. So let me come back to the document cam for a moment, so that frees up the cameras for Jennifer. And here's what's done as we come off there. And I hope you aren't resorting to this. I'm sorry. This would just break my heart. N over N, giving you N, which is n to the 4th. Please subtract exponents. Now what's not clear is that 2.5 is going to go into 8.2 3.28 times. Okay, so enough said there, I hope. A problem like this. Negative 14.2x equals 39.05. Just tell me what to do quickly in 5 seconds. Top of the screen. I'm on page 447.
Move the decimals over 1.
No, tell me operationally what to do. Divide both sides by the coefficient. This is what I think, Kim, was your favorite approach with fractions. Divide the left side by negative 14.2, and the same there. There's showing it better than I can say it clearly, and you get your answer. The bad part of this, the decimals are not fun to do longhand. So I'm going to spend some time going through some of these problems tomorrow as part of our tutorial. The quiz we have tomorrow will cover sections 6.1, 6.2, and 6.3. I don't think I'll try to do anything with 6.4 for tomorrow.
Thank you very much.
You're welcome. So with that, we're going to come back to the infamous Bruce. And what